Hey guys, in today's lecture, we're going to talk about fluids. We're going to just cover static fluids today, and then in our next video, we'll go over fluids in motion. But there's a few concepts we haven't talked about yet that we first need to cover before we really start working with fluids. And our goal today is going to be looking at this situation. If this is some object in some fluid, um, we want to figure out if it's going to sink or float. And if it's floating, maybe how much of the object sticking out of the water we could figure out. And so, in order to do so, we're going to have to use a few new concepts, like I was saying. One of them that I mentioned is density, which I've talked about several times throughout the semester, but we kind of just ignored what it was and didn't really go into much depth. But density is just the mass of an object divided by its volume. And this is going to become, you'll see, very helpful when we're dealing with fluids. We're going to be able to compare the density of some object to the density of whatever fluid is in. Generally, we're going to talk about water, but it could be any fluid. And when we compare these two, the density of some object to water, it becomes easy to figure out if something's going to sink or float. And then depending on the shape of the object, we could figure out if it's floating, how much it's sticking out of the water. So another physical concept we haven't talked about is pressure. So we've always been talking about forces, right? Where we have some force being applied to a object and we solve problems that way. Well, when we're dealing with fluids, we generally, instead of talking about the force of something, we talk about its pressure, how it's distributed over an area. So instead of just thinking of this force being one point force, we could think of it being spread across an entire area. And so this upside down T is just for the force perpendicular to the surface, because we just want the force that's being applied to the surface. And what we see is that pressure is just going to be our force divided by an area. So whatever area that this force is being spread over will quantify our pressure. It kind of gives a uniform force throughout an area because it's force over an area. So if we follow our units, we could see here in the numerator we got force. So our numerator's units are going to be newtons. And in the denominator we have area. So when we're dealing with our base SI units would be meters squared. And so the units we're going to work in physics for pressure are called pascals. There's many different units. When you're dealing with pressure, you'll see there's psi, bars, atmospheric, millimeters of pressure, millimeters of mercury, and there's many more. But we're going to be, for the most part, dealing with pascals, which is just newtons per meter squared. So let's apply these two concepts and try to figure out, if we're given this object, we have some box, and we're told its dimensions are 2 meters, the width, the depth is 3 meters, and it's got a height of 1.5 meters. And if we're told the density of this object is 2.7 times 10 to the 3 kilograms per meter cubed, what is the pressure that it's being applied to our surface, where this box is contacting whatever surface it's resting on? Well, before we would have looked at force, and we would have said that our force is just mass times gravity, right? But now we have the dependency of how this force is being spread out to consider our pressure. So all we would need to do is divide our, if we could get the force downwards and divide by our area, surface area, contact area, we'll end up with our pressure that this object is applying on its surface that it's sitting on. So we got pressure equals force divided by our area. And of course, our force is going to be mass times gravity. And our area is going to be our width of the box multiplied by the depth of the box. And so our mass, we're not given in the problem, right? But we know from our density equation that our mass is, if we just multiply our density by volume, we'll end up with a mass. So we're just substituting rho v for mass in this equation, which gives us a pressure is equal to the density of the object, in this case, multiplied by its volume, multiplied by gravity, and divided by its area. But volume is just our base times our height, right? Our width, depth, and height, ABC, I have it represented. So our A and our base and our depth, or whatever you want to call it, and of this object will cancel in the numerator and the denominator. And so what we see here is that our pressure of something is only going to be dependent on our density of the material multiplied by the height of that material multiplied by gravity, which comes in handy once again working with fluids, because you could think of talking about, let's say if you're talking about the pressure at the bottom of the ocean, this gives us a easy way to talk about quantify that, because it's only dependent on how deep you're going in the ocean. We don't care how wide the ocean is. If let's say a swimming pool's got a radius of 20 meters or 100 meters, but it has the same depth, we're going to have that same pressure at the bottom of the pool. So this gives us a way to talk about force without having to consider everything in it. It's just in a vertical column upwards is what our pressure is going to be dependent on. So we get rid of two dimensions that we need to talk about. So back to the problem, we could plug in our values from before, all of our known values. We got the density of the object, the height of it, and gravity. And this comes out to be 3.97 times 10 to the 4th pascals. So in this example, it will demonstrate how helpful it is being able to work with pressure instead of force, because we're only worried about the height of something. So what I have drawn here is a container, and we have two layers. We have a layer of fluid down here. We don't know what it is. And we have a layer of fluid here. Well, if we're told, given these values of we have some pressure at the bottom of this tank of 1.3 times 10 to the 5 pascals. And we are told the height of each fluid, height 1 is 1.9 meters, height 2 is 2.2 meters. And we're told the density of fluid 2, this fluid on the top, 500 kilograms per meter cubed. What we want to find out is what is our density of our fluid 1 down here, this lower fluid. So what we saw before is that our pressure is dependent only on our height and the density of our fluid. So when we solve this, all we have to do is add up everything that's above this, the height of it, and the height of it multiplied by the density of that object multiplied by gravity. But one thing we also have to take in consideration is that we don't just have fluid, two different fluids, a layer of fluid here, a layer of fluid here, and that's it. We also have fluid above this, from the molecules in the air pushing down on top of this surface. So we need to also consider that. So that's our atmospheric pressure. And since we're not going to calculate the pressure, we're just going to use that atmospheric pressure as 1.01 times 10 to the 5 pascals. And so whenever we have an open container like this, we need to consider the pressure outside of the container if it's an open container, because that's going to also add to the total pressure at the bottom of this tank. Because if you think about it, if we drain this tank and only had atmospheric pressure, we would still have that pressure, atmospheric pressure, at the bottom of the tank. And then we are now just adding more fluid on top of that. Okay, so we know that our pressure is dependent on our density times gravity times our height. We saw that in our last example. And since we have 3 different layers, we could just sum each of these individually. The density of 1 times the height of 1, the density of 2 times the height of 2, and then we have to add our atmospheric pressure, which once again, we're not dealing with the density and the height. We're just told whatever the pressure is from it. So this would have been equivalent to the density of air multiplied by the gravity multiplied by that column. But the problem is with air is that its density is going to change with height. So we're just going to use the 1.01 times 10 to the 5 pascals for atmospheric pressure. So we have the sum of each component that's contributing to this pressure at the bottom of the tank. So we should be able to just solve for our rho 1 now, right? Because we know what gravity is, we're told what height 1 and 2 are, and we're told what density 2 and pressure is. So our only unknown value is rho 1. So we could subtract over our atmospheric pressure and our pressure that comes from our second fluid, the upper layer. Oops, sorry. And then we can divide by gravity and height 1, and we'll be left with the density of fluid 1, which is what we are looking for, this density of this fluid. So plugging in all of our values that were given, we got our pressure at the bottom of the tank minus our atmospheric pressure minus the pressure from fluid 2, and then we're dividing by gravity and the height of fluid 1. And this gives us a value of 977 kilograms per meter cubed. So how does knowing the density of an object help us know if we are going to take a object and throw it into some fluid, if it's going to sink or swim? So let's work through this problem and hopefully it will become clear. So we're given a, let's call it a rock, I guess. It has a volume of 0.23 meters and a mass of 300 kilograms. And so what happens when we throw this rock into the water is that the water is going to be trying to push in and get where this rock is, right? And this is going to result in a what we call a buoyant force. So we have the force of gravity that we know is just going to be mass times gravity pulling this rock down into the water. But this water is trying to get in there as well because it's being pulled down, and this results in a upward force, and that is known as a buoyant force. And our buoyant force is equal to our density of our fluid displaced multiplied by the volume of the fluid and multiplied by gravity. So our buoyant force isn't dependent on the mass of the object that's being submerged. It's only dependent on the how much volume this object displaces. And so if this object sinks all the way, if it sinks down to the bottom of this container, we know that the volume being displaced by the object in the water is going to be the same as the volume of the object itself. But if this object is floating on the surface, we no longer have displaced the entire volume of this object. We've only displaced whatever portion has been submerged. So if we sum our forces and think about F equals ma, if our buoyant force is greater than our force from gravity, this object's going to float because we have a net upward force. But if the force of gravity is lower than or higher than the force of the buoyant force, it's going to sink. So we could say if buoyant force is smaller than the force of gravity, our object will sink. So let's see how we can come up with that. Okay, and so this equation that just popped up, my program's running slow, is just our force from gravity. So our buoyant force was our density of the fluid being displaced, the volume of the fluid being displaced times gravity, and our force of gravity is just our volume of our object times the density of the object, which is just mass, and then we're multiplying that by gravity. All right, so if we take the ratio of these two objects, we know that if gravity is greater than our buoyant force, our ratio will be greater than 1. So if it's greater than 1, our object will sink this ratio. And if it's less than 1, our buoyant force is bigger than our force of gravity, so we know our object will float. Is why I set it up in this ratio. So in this case, so here in this case, our volume of our object is going to be equal to the volume of the displaced fluid. And that's because when we compare if we multiply our density of our fluid, which is just our mass divided by our volume, it comes out to be 1,304 kilograms per meter cubed. And if we look at the density of water, it's 1,000 kilograms meter cubed. So if we compare the density of these two, our density of our rock is going to be greater than our water, which means even if our volume, so looking at this ratio here, the reason we come up with this, our volume of our object is equal to our volume displaced, is because even if so basically the volume being displaced can be a maximum of the volume of the object. So if we maximize this value and multiply by our density, it's still going to be a smaller value than if we multiply our density of our object by our volume. So it turns out that these volumes in this situation are going to be the same. Basically, the buoyant force, there isn't enough volume for the buoyant force to take over and make this object float. So we could simplify this, canceling our volume, since they're equal to each other, and gravity obviously could cancel because we have it in the numerator and denominator. And what we end up with, is the mass of the object divided by the volume of the object, which is just the density of the object, divided by the density of the displaced fluid. In this case, it's water. And so if we plug in our values, we see that our density of our object is not our density, the ratio of our force of gravity and our force of buoyancy. Hold on one second. Sorry about that. All right, so our ratio of our force of gravity divided by our buoyant force is going to be equal to 1.304, which this ratio, as we saw, is just equal to the density of our object divided by our density of our fluid displaced. And so there's this concept called specific gravity. And when we take the ratio of some density of some object and divide it by the density of water, this is known as specific gravity. And so this comes in helpful because if we look at the ratio of these two things, and the specific gravity is greater than one of an object, the object will sink in water. But if the specific gravity is less than one, the object will float in the water. Okay, so now let's look at a video where we're told that an object is floating, and we're told that it has some height submerged underwater, 0.33 meters, and we have a height of 0.45 meters above the water. And it's in water, so we know the density of water is 1,000 kilograms per meter cubed, and we want to know what is the density of this object. Well, from that last example, we know that the density is going to be less than 1,000 kilograms per meter cubed. Otherwise, it wouldn't be floating, because that ratio of the density of this of the object divided by the density of water has to be less than 1 for this to be floating. So we know this is going to be less than 1,000 kilograms per meter cubed, but we don't know what that is. But what we talked about also in that last video is that this water being displaced is so basically we have our force of gravity on this object pulling it downwards, and we have this buoyant force. Well, this water is trying to get in here and replace this volume this box is, and it's pushing, creating that buoyant force upward. And so what we saw in the that last example is that our mass of the object, our buoyant force, has to be equal to our force of gravity if it's floating, because we're not accelerating, right? And so the volume of the water displaced multiplied by the density of water should be equal to the mass of this box. And we know that our density of our object is just our mass of the object divided by the volume of the object. Well, in this case, like I was just saying, our mass of the object could be represented by the volume displaced of the fluid, which is water in this case, multiplied by its density. So it would be this little submerged part, volume, multiplied by the density of water. So if we substitute that in for our mass in this equation, we end up with a density of our object equals the volume displaced, the density of water divided by the density of our object, and this will give us our density, our density of the object. This is volume. I think I said density a second ago. Anyways, so the volume being displaced of water is going to be equal to the width, the length, multiplied by the height submerged, this HS, and that's the volume displaced. So we could replace our volume displaced by the width of the box, the length of the box, and multiply by the height submerged. And then we're still multiplying by rho of the water. In the denominator here, we had the volume of the object, and that's the entire object. So we have the same width and length. We weren't given this, but as you can see, it's going to cancel here and here, so that's good. But then we have the height of the object, which is the height submerged plus the height I put a subscript A for above the water. So if we simplify this, we could get rid of our width and our length, and we're just left with, in the numerator, the height submerged times the density of water divided by the height of the entire object. So we could plug in our values. We had the height submerged was 3.3, and the height above the water is 0.45 meters. And then our density of water is 1,000 kilograms per meter cubed. And this comes out to be rho. Density of the object is 423 kilograms per meter cubed. And as we predicted from the get-go, from that previous example, we knew our density needed to be less than 1,000 kilograms per meter cubed because the ratio of our density of object divided by water had to be less than 1. So we know that this result makes sense. Or at least hopefully it makes sense. So hopefully from today's video, looking at our formula sheet, down in the bottom right corner it says fluid and pressure. 3 of those equations, the bottom right 3, we have density equals the mass divided by volume, pressure equals the force, perpendicular force applied to an area, and we have the specific gravity is equal to the density of an object divided by the density of water. And once again, if specific gravity is greater than 1, the object will sink. If it's less than 1, it will float. So in our next video, we'll continue with fluids. We're going to talk about fluid in motion and the different properties of that. So if you have any questions about this video, if I screwed something up along the way, let me know and I'll address it. And then after our next video, I'll do another video just working kind of some random problems of fluids and talking about anything else that we might have missed. And I'll be unlocking the homework shortly, so keep your eyes open for that. Take care.